variation inside the data. Okay, you can capture this variation by adjusting the direction of your line. So the original data are projected into a smaller space, which results in dimensionality reduction. Okay, so if you see the original data, now this original data, if you see, it is represented in 2D. Okay, you have X and you have Y. You have XY plane. Now this data can be on the either X or Y side. And then you can represent it by reducing the dimension, and you can represent it in the straight line. So we find that the eigenvectors of the covariant matrix and these eigenvectors define the new space, okay, which is the reduced space. So there are several steps for principal component analysis. The first one is that if you have a given data vector for n dimensions, we want to find a k which is not equal to n, which is always less than or equal to n, not greater than m. So these k orthogonal vectors are known as the principal components, and they can be best used to represent the data. The next step is to normalize the input data, where we fall the data into some range, and then we compute the k orthogonal vectors, which are the principal components, and each input data vector is then the linear combination of k principal component vectors. So the principal components are sorted in order to decrease significance or the strength. In order of decreasing significance or the decreasing strength, and then the components are sorted, the size of the data can be reduced by eliminating the weak components. Okay, so you can just go through these steps once again. So first we normalize the input data, then we compute the k orthogonal vectors, then each input data is a linear combination of the k principal component vectors. So the principal components are then sorted in order of decreasing significance of strength, and then the highest are selected and the weakest are discarded. Now the second step could be attribute subset selection, which is another way to reduce the dimensionality of the data. So we have some redundant attributes which are the duplicates, and these have we can duplicate much or all of the information contained in one or more of their other attributes. So then there are some irrelevant attributes. They contain no information that is useful for the data mining task. For example, student ID is often irrelevant to the task of predicting the student's GPA, as we discussed in the class as well. And duplicate data, on the other hand, are the redundant data attributes, and they are contained in one or more places. For example, purchase price of a product at the amount of sales tax paid. Okay, so it is duplicated in the tax return and the amount when you paid it. Okay, so now we have to select the attributes which are relevant. Okay, we do not want to select the redundant attributes, or we do not want to select the irrelevant attributes. Okay, so there are many techniques for attribute selection. The first one is heuristic search technique, and there are 2D possible attribute combination of D attributes. Then typical heuristic attribute selection methods, we have the best single attribute and the attribute independence assumption, and then we can have best stepwise feature selection, where the best single attribute is picked first, then next best attribute condition to the first, and then so on. So it's a stepwise attribute elimination method is also there, where we repeatedly eliminate the worst attributes. Then we have best combined attribute selection and elimination, and then we can have optimal branch and bound conditions. So attribute creation, first we were selecting the already present attribute. Now we can also create the attribute. Okay, so there could be several techniques for doing so. Okay, so we can create new attributes that can capture the important information in a data set. Okay, and this information can be captured in more efficiently or effective manner as compared to the original ones. So three general methodologies are there. We can extract the attributes from the given problem domain, or we can map data to a new space, or we can have a construction of the attributes where we can combine different features, patterns, and these are discussed in an advanced classification chapter later on in the course. Now, if we want to compare two different attributes, two different properties of objects, so we can have some measurement which can measure these properties, okay, which can measure the differences between two different objects belonging to different classes. So one of these objective measure which can measure these things could be the similarity measure. How similar one object from one class is to another object from the another class, or how similar two objects of the same class are. So there we need to define some similarity measure. So it is a numerical measure of how alike two data objects can be. So it is higher. Similarity between two things is high when objects are most likely each other. Okay, when they are the same, and it is the lowest when the objects are most dislike. They are not alike. Okay, they are disalike. So it often, therefore, similarity can be, we can measure the similarity in the range of 0 and 1. If two objects are not similar, we will say it's 0. And if they are 100% similar, same to same, then we will say it's 1. And the intermediate range can lie between 0 and 1, like 0.7, 0.5, 0.4, and so on. Now, dissimilarity is a numerical measure of how different are two data objects. So it is lower when objects are more alike. It is the vice versa of similarity measure. So the minimum dissimilarity is often 0, and the upper limit varies. So proximity refers to a similarity or dissimilarity of two objects. Now there are several different equations, different formulas. We'll skip these for dissimilarities and similarities. Also, we can use the distance between the two features. They can give us the similarity or dissimilarity between two objects. So we can have Euclidean distance, which is a simple distance, and this is the expression and the results. Then we can have a Minkowski distance, or we can also call it a generalization of the Euclidean distance. So you can see the expression for this type of distance. Okay. Then we have another type of distance which is known as the city block distance, or we also call it the Manhattan distance, or taxi cab distance, or L1 normal distance. So it's a common example of this is the Hamming distance, which is just the number of bits that are different between two binary vectors. Okay, then this is how the Minkowski distance. And then we have another type of distance which is given by this expression. It is called, it is known as Mahalanobis distance. Mahalanobis distance is given by this expression over here. So it also measures the similarity or dissimilarity between two different objects. Okay, so you can have a covariance matrix, as you can see, and from that you can find the distance. So common properties of a distance. So distances such as Euclidean distance have some very well-known properties, and these are given by these equations. You can go through these. So similarity are also some well-known properties, for example, which are given by these equations. Okay, so then there is similarity between binary vectors. So common situation is that two objects P and Q have only binary attributes, and we can compute the similarities using the following quantities, and these can be seen from these expressions. So simple matching could also be there in the form of Jaccard coefficients, and it is given by this expression. Then we have another type of similarity which is known as cosine similarity. So D1 and D2 are two document vectors. Then cos of D1 D2 is equal to cos of D1 dot D2 oblique or divided by modulus of D1 into D2. So where dot indicates vector dot product and D modulus is the length of the vector D. So you can see this example how it works. Okay, then the second thing is in data reduction is numerosity reduction. We know that numerosity reduction means that we reduce the size of the population. So we reduce the data volume by choosing some alternative smaller forms of the data representation. For example, we can take some sample of the data. So there are some parametric methods, then we have some non-parametric methods for numerosity reduction. So in parametric methods, we assume that the data first fits into some model, and then we estimate that model parameters, and after that we store only the parameters and discard the data. For example, we have some models, you might not be knowing that at this stage, but there are models like log linear model where we obtain value at a point in MD space, and it is a product on appropriate marginal subspaces. Then we have some non-parametric methods. For example, these parametric methods are well known, and they are not based on any model. For example, the histograms, the clustering methods, sampling methods, these are all non-parametric methods. Okay, in this there is no underlying model. So if a question comes in the examination, what is the difference between parametric methods of and non-parametric methods of numerosity reduction, you can know that one is based on some model and the other is not based on some underlying model. Okay, so first we cover the parametric data reduction models or methods, and the first one is regression and log linear models. So regression is also of many types, for example, linear regression and multiple regression, and then we have some log linear model. So linear regression is a type of regression method where data is modeled to fit a straight line. Okay, as the name suggests, linear regression. So data is modeled so that it can be fit, the curve can be fit on a straight line. So it often uses the least square method to fit the line. Then we have multiple regression, which allows a response variable y to be modeled as a linear function of multi-dimensional feature vector. Okay, so you can have a multi-dimensional vector and then you can have a response linearly recorded, so that it have multiple times of linear regression. Okay, then we have log linear model, which approximates the discrete multi-dimensional probability distributions, okay, by using the log linear functions. Okay, so we can also see how regression works. So regression analysis, it's a collective name for technique for the modeling and analysis of numerical data, which consists of values of a dependent variables, and this is also known as a response variable or measurement variable, and of one of or more independent variables, for example, explanatory variables and predictors. So the parameters are estimated so that it can give a best fit of the data, and most commonly the best fit is evaluated by using some least square methods. Okay, and other criteria are also there. So this is an expression for, you can see, linear regression, and then we have multiple regression, and then we have some log linear models. And the next thing is the histogram analysis, where we divide the data into some buckets and store the average or the sum of these buckets. or we can sample the data into some equal intervals, as you can see on the x-axis of the graph. And the partitioning rules is that equal width can be there where equal bucket range is there, or you can have an equal frequency or equal depth in the partitioning. Okay, then another technique is known as clustering, where we partition the data into clusters based on similarity and store the cluster representation only. So it can be very effective if data is clustered, but not if that data is smeared or which is not clustered. We can have some hierarchical clustering and be stored in multi-dimensional index tree structures, and there are many choices of clustering definitions and clustering algorithms which we can choose from. And the cluster analysis will also be studied in detail in chapter number 10, I think, most probably after the midterm examination. Okay, so the next thing is sampling. Sampling, you mean, you know that in sampling we just select some sample from the population or from the data, entire data. So when we are obtaining a small sample S to represent the whole dataset N or the population P, we say that we are sampling something. So it allows a minimum mining algorithm to run in complexity that is potentially sublinear, which is less than the size of the data. So the key principle of sampling is to choose a representative subset of the data, and we can do it by simple random sampling, okay, or you can where we choose a representative subset of the data, and you can also develop some adaptive sampling methods, for example stratified sampling. We will discuss it sooner. So sampling may not reduce the database input outputs. Okay, so there are some types of sampling, for example simple random sampling, sampling without replacement, sampling with replacement, and stratified sampling. So simple random sampling is that we randomly choose the variables or the points or the samples from the data. And sampling without replacement means that we choose one sample from the data and we do not replace anything instead at the place of that data. Okay, for example, if the data size is 100 and we take out one sample, the remaining data size will be 99. Then we take another sample, the remaining data size will be 98, and so on. The second technique is opposite to sampling without replacement, and it is known as sampling with replacement, where we select something, some object, and if it is removed, we replace it with another object in the population. If you choose something from 100 and the remaining are 99, then one more thing is added from the generated from other data so that it remains 100. The last type of sampling is known as the stratified sampling, and in this we partition the dataset and draw samples from one from each partition of the data, so we have the representative from all sides of the data. Okay, like for example, if you want to have some survey of the population of Saudi Arabia, you can divide the country into different parts and have some samples from each corner of the country, okay, from north, from south, from east, from west, and everywhere, and from the center. So this comes in the sampling, stratified sampling. Okay. As you can see that there is raw data, you have made some different parts, and from each part now you have a cluster or stratified sample of that portion, the region of the data. Okay, data cube aggregation, we will have a complete lecture on data cube, so we'll just go through it now. So the lowest level of a data cube is known as a base cuboid. We'll discuss what a cube is, and the aggregated data for an individual entity of the interest is known as a data cube. For example, a customer in a phone calling data warehouse, he has some information which will be represented in the form of data cube. How this we will discuss in the next coming weeks. Okay, we have a complete lecture on how data cube works and what is the data cube all about. Now, multiple levels of aggregation in the data cubes can be there. We can further reduce the size of the data to deal with it, and also we have some reference appropriate levels where we use the smallest representation, which is enough to solve any given task. And there are some queries which are based regarding the executed information, and they should be answered using the data cube whenever it is possible, and it becomes easy and fast in the data warehouse. Okay, now the third type of data reduction is data compression, and we all know what compression is. So compression is about reduction in the size of the data by compressing the data. Okay, so there are extensive theories and well-tuned algorithms. For example, typically lossless compression is there. Okay, we can have a compression in strings, we can have compression in audio and video, we can have compression in images, we can have compression in time sequences or time series. Okay, there are many applications of compression. So also we can have dimensionality and numerosity reduction, which also may be considered as a form of a data compression, because we are reducing one dimension and so thus we are compressing the data. Okay, and let me involve you guys as well. You are so silent. Yes, you are coming and going into the room. Okay, so who will give another example of any compression techniques or the applications of compression? Okay, can anyone give an example of any compression technique which is not here, written here, or the application of compression which is not written in the slide? Please take some time and think over it. Yes, good. WinRAR is one example of compression. Then we have zip and JPEG. Yes, 7-zip. Okay. Yes, good. It means that you are with me. Okay, tar is another example. So this diagram represents data compression. We have original data, we compress the data. There is some loss of information, and we have an original data approximated. So why approximately? Sorry, approximated, because there is some loss due to compression. Okay, this information is lost, so it does not belong. The data does not contain this information. So we say that original data is approximated by the compressed data. You see that if a bitmap image is compressed using a JPEG standard, you will not notice a very visual change in the data. But if you very minutely examine the images, so you will see that there is a difference in quality of the image in JPEG as compared to the bitmap. Bitmap is 100% the original quality, but JPEG is a reduced or compressed version of the original. So if you very keenly observe, you will find some difference in the quality of the compressed data. Okay, now the last topic of this week is data transformation and data discretization. Data transformation is a function which maps the entire set of values of any given attribute to a new set of replacement values, so such that the old value can be identified with the one of the new values. So we transform the data. You take it from one domain into another domain. So there are several methods for transformation. For example, smoothing, which removes noise from the data, or attribute feature construction, where new attribute constructed are constructed from the given ones. We can have aggregation, where we summarize or construct the data cube. We also have normalization, where we scale the data to fall within a smaller specified range. Then we have minimum and maximum normalization, z-score normalization, normalization by decimal scaling. These are all normalization types. Okay, then we have discretization, where we have a new concept which is known as concept hierarchy climbing. Okay, so don't get afraid by looking at the names of the things. When you'll see, you'll understand that they are easy, and most of the mathematics we are not covering. Okay, we won't give the mathematical equations in the examination. You do not have to learn them by heart. So normalization has many types. For example, the first one is minimum maximum normalization, and you can see its equation over here, and the example is that if you have an income range from 12,000 to 98,000 and you want to normalize it between 0 and 1. In normalization, we transform the data into some another scale. For example, in this example, we are transforming the data from 12,000 to 98,000 into 0 to 1. Okay, so we are just transforming this range, which is given by 12,000 to 98,000, to another range which is given by 0 and 1. So then 73 is mapped into this new number, which is 0.716. Now this is the normalized data. In the range of 0 and 1, 0.716 is similar to 73,000 in the range of 12,000 and 98,000. You understand? So this is known as minimum maximum normalization. We have a minimum point, we have a maximum point, and we normalize all the data in between this minimum and maximum point. Now if for this example, if someone says, okay, normalize the 11,000, so we cannot normalize that because we have not defined that its range. Okay, our range only covers the minimum value is 12,000 and the maximum value is 98,000. The second type of normalization is known as the z-score normalization, where we have the mean, which is given by mu, this u looking this symbol which looks like a u or micro. So mean and sigma. Sigma is the standard deviation. So this is the equation for z-score normalization. Again, we have some value for mu and sigma, and we can then scale the normalization according to any number. Okay, then we have normalization by decimal scaling. This is the expression where j is the smallest integer such that the maximum of v bar modulus is less than 1. Okay, now the next topic is about discretization. We can discretize some things. Okay, we can discretize things into some samples using some sampling. Okay, I hope you know about discretization a little. For example, when you have a continuous signal and you convert it into a when you have an analog continuous signal alhamdulillah, and you convert it into a digital and you want to convert it into a digital signal, the first step is to you chop the signals at equal intervals or equal samples. So this chopping means that you are making it discretized. You are discretizing the signals. Okay. So there are three types of attributes. We have nominal attributes, we have ordinal attributes, and we have numerical attributes. So nominal attribute values are from an unordered set, for example, color and profession. We have discussed this in the previous lectures. Ordinal values from an ordered set, ordinal as the name ordinal suggests, and numeric contains some real numbers, for example, in the form of integers or any numbers. Okay, so discretization means that we divide the range of a continuous attribute into some equal intervals or into some equal samples. So equal interval or interval labels can, or the sample labels can then be used to replace the actual data values. So you can reduce data size by discretization, and it can be in the form of supervised or unsupervised discretization. It can be in the form of split and merge. For example, split is top-down and merge is the bottom-up discretization. And discretization can also be performed recursively on any attribute. And okay, we can use this technique of discretization to prepare our data for any further analysis in the data mining task. For example, for classification, we can use it. Now there are many data discretization methods. Some of these are discussed over here in this slide. So typical methods, which are all methods, all of these can be applied recursively. So the first one is binning, which is a top-down split or unsupervised learning algorithm. And then we have histogram analysis, which is a top-down split, or again it is unsupervised. Then we have clustering analysis, which is unsupervised top-down split or bottom-up merge, and these are clustering analysis. Then we have decision tree-based analysis, which are supervised, and they are also top-down split. Then we can have correlation analysis or correlation tests, for example, the chi-square test. This type of discretization method is also unsupervised, and it is a bottom-up merge. Okay, so also we can have different discretization in the binning. For example, we can have equal width or equal depth. Width is also known as the distance, for example, in the sampling, and depth or the height of discretization is also known as the frequency or frequency partitioning. So in equal width, we divide the range into n intervals of equal size in a uniform grid. And if A and B are the lowest and highest values of the attribute, then the width of the interval will be given by this equation. It's very easy and it is more straightforward, but outliers may dominate the presentation. Okay, and it is also in this skewed data is also not handled very well. The other type of discretization is equal width discretization, or we can also say, sorry, equal depth discretization or equal depth based partitioning, and we also call it frequency based partitioning. In this, we divide the range into n intervals, and each contain approximately the same number of samples. So all the intervals will have the same number of samples. So it is good for data scaling, and it is also good for managing categorical attributes. And but this managing of categorical attributes can also be sometimes very tricky in this type of partitioning. Okay, so there are some binning methods and sorted data for price in dollars. You can see that there is sorted data. So you can partition into equal frequency, equi-depth bins. For example, you can write 4, 8, 9, 15. So this is in bin 1. So 4 elements in all the bin. And then you have another bin which is bin 2. In this you can put 21, 21, 24, and 25. And then you can have bin 3. In this you can put 26, 28, 29, and 34. So you have equal frequency or equi-depth bins. And smoothing by bin means that you can have some smoothing by applying the average, and you can see that now there is a change. Now smoothing by boundaries is given by this. Okay, we'll cover this in detail when we will discuss about the bins. Now the next topic is discretization by classification and correlation analysis. So classification can be a lot, different numbers of classification algorithms and techniques are there. So we'll see that we can have, for example, decision tree analysis, which is supervised, and we have some given class label. Okay. And we can use entropy to determine the split point, where we can split the classes into 2 different classes. Okay, and then it can be a top-down approach, and it can be the recursive split. So the details are covered in classification chapter that we will cover soon, inshallah. The second type of discretization by classification and correlation analysis topic, the second type of analysis is by the correlation. As we discussed that we have chi-squared based discretization, we have some other statistical techniques as well, like chi-merge. So supervised, it is supervised and it uses class information. So we have bottom-up merge where we find the best neighboring intervals, so which have the similar distribution of classes. For example, low chi-square values to merge, and we can also merge recursively until a predefined stopping condition is met. Okay, now the last topic is about concept hierarchy generation. Concept hierarchy, it organizes the concepts or the attribute values hierarchically and is usually associated with the dimensions in the data warehouse. Now these types of hierarchies, they facilitate the drilling and rolling in the data warehouse. We will see in the coming weeks what drilling and rolling is, and you must have studied this in the databases as well, and to view data in multiple granularities. Now the concept hierarchy is done by recursively reducing the data by collecting and replacing some low-level concepts such as numeric values for age by higher level concepts such as youth, adult, and senior. Okay, so you will remove the low level concepts and just give the higher level concept. Okay, you will remove the values and give it a concept. That is a very easy thing. For example, if you have age of 8, you will say youth. Okay, you have age of 9, it is still youth. Okay, so data and the problem is much reduced by including the concept hierarchy. And the concept hierarchies can be explicitly specified by domain experts or some data warehouse designers, and these hierarchies can be automatically formed for both numeric and nominal data. Okay, so we can have discretization methods as shown in the previous slides. For nominal data, we have some other methods which we will discuss soon. Okay, so this yes, data mining is a little heavy. Okay, so this completes our today's task. And if you have any questions, please ask them. Inshallah, this week I will try to upload all the slides and make a link for the slides in the Blackboard. Yes, it is. There are some terms, and you have to go through them. Yes, we have a lot of different terms in this course. Because it's a combination of many different fields, this comes on the intersection. This course comes on the intersection of a number of fields. So you'll have some different things from different areas of science. No, you do not. I've repeated again and again that you do not have to remember the formulas. Okay. We will not give you the formulas to memorize and reproduce them. Okay, so just for your understanding, go through the formulas, and we will not give them in the examination. Don't worry about remembering these formulas. Okay, so if you do not have any questions, let's call it a day then. Have a nice weekend. Inshallah, we will meet in the next face-to-face class on the coming Sunday, sorry. Okay, thank you and good night. Have a nice day. Inshallah, see you next week.